Hi everyone, my name is Runtian and welcome to this talk on generalized skyline interval coloring and dynamic geometric bin packing problems. To begin with, I want to first introduce cloud computing, which is the application of the problems. Well, during the past decade, many companies have moved their business onto the cloud, and the most famous cloud service providers are Amazon and Google and Microsoft. Well, the most salient feature of the cloud computing is the pay-as-you-go billing mechanism. One issue faced by the customer is how to dispatch a set of jobs onto the cloud servers such that the total rental is minimized. For example, suppose I am a company and I rent virtual machines from Amazon to run several jobs. Here we use the rectangles to represent the virtual machines of the same type, and the virtual machines have the same capacity because they have the same computational resources like CPU and GPU, and also they have the same renting cost rate. And now suppose my first two jobs arrive at time zero. Since they have their total size exceeding a virtual machine's capacity, I don't have another choice. I have to rent two virtual machines for dispatching them. And later, a third job arrives, and then the first job also arrives. One trivial dispatching solution could be like this. In this way, I got to pay a total cost equals to 12 hours times the renting cost rate to Amazon. On the other hand, I could change my dispatching strategy like this to save some cost very easily. So this suggests that a good job scheduling strategy can indeed help on minimizing the cost to rent the virtual machines under the pay-as-you-go billing mechanism. Such an issue is modeled as a combinatorial optimization problem, which is called mean usage time dynamic bin packing, and indeed have been studied extensively since 2014. More formally, the input is a set of jobs, interval jobs, of course, and each is specified by an active interval and a size. So these jobs are to be processed by the machines with the same capacity 1. The restriction is that at any time, the jobs placed onto the same machine cannot exceed the machine's capacity, which is 1. And the target is to minimize the total busy time of the machines used for running all the jobs. Alright, so such a problem called mean usage time DBP has been considered under the online and the offline situations, and for each situation, a near optimal algorithm has been proposed. Okay, now we reach the topics we are really interested in this talk. We want to consider a strict version of the previous mean usage time DBP problem, which assumes that each job must be assigned a continuous memory of its size for its execution when running on a machine, and no two jobs can share the same memory when running concurrently on a machine at any time. So here I want to stress that such a stricter assumption indeed make a difference from the previous mean usage time DBP. For example, under the model of mean usage time DBP, such a job J can be placed onto the machine M in a feasibly way, but under the strict assumption, such a job can only be feasibly assigned to machine M in the case on the right side, because there is no continuous range of J size in machine M on the left side case. We name this problem as dynamic geometric bin packing, since each feasible solution can be illustrated geometrically. And by the way, here I want to remark that each feasible solution of DGBP must also be a feasible solution of mean usage time DBP, but this doesn't hold true on the contrary. We also consider another variant problem called generalized skyline interval coloring. We ignore the machine's restriction and we focus on seeking an allocation for all the interval jobs such that accumulated cost produced by this allocation is minimized. We consider the problems under both offline and online settings. We focus on proposing approximation algorithm for the problems in the offline setting, and in the online setting, there are two different flavors, non-clairvoyant online and clairvoyant online. We first talk about the definition of non-clairvoyant online setting. That means the jobs are released in the order of their arrival times, and once a job arrives, its size is known, but its departure time is not known. Under such situation, each job still has to be assigned to a machine at its arrival immediately with no information of the future jobs and even its departure time. While in the clairvoyant online setting, it is much better. When a job is released, its arrival and its departure time and its size are all known. Remark that the jobs may be not released in the same order as their arrival times in such clairvoyant online setting. Still, each job has to be assigned to a machine once it is released without the information of the job's release in the future. So there exists some previous work for the mean usage time dynamic bin packing problem, and some of the results help on establish the lower bound on the competitiveness for DGBP. Also, a previous work considered the Skyline interval coloring problem, which is a special case of GSIC by assuming that each job has the same size 1. One previous work suggests that no deterministic online algorithm can achieve a competitive ratio less than log mu for our generalized Skyline interval coloring. In this work, we design algorithms with their performance ratio matching the lower bounds, and for each problem in each setting, we propose nearly optimal algorithm. Most importantly, we found a uniform recipe to propose this well-performed algorithm, which is called aligning. Yeah, so this is much about the aligning technique. That picture, in fact, summarizes precisely. That means given any interval job with its interval under one of these three cases, an aligning job shall be constructed accordingly. And we can make sure that the length of a job is not enlarged too much on one hand, and we also make sure that the arrival time and departure time of the job constructed is very regular on the other hand. Furthermore, we can make sure that any feasible solution for the aligned instance is also a feasible solution for the original instance. That means all we need to care about is to find a good solution for this aligned instance. By applying the aligning technique, the jobs can be classified into two categories, regular and irregular. We will use these two notions often in the following slides. We first talk about the offline generalized Skyline interval coloring. Our strategy is to schedule all the aligned jobs in the decreasing order of their lengths. That is, we first pile up the longest regular jobs, and then we pile up all the longest irregular jobs. After that, we shall pile up the second longest regular jobs, and so on. This strategy will for sure produce some waste, like shown in this picture, but fortunately, the waste area is no more than a constant amount of the total job area. And that is mainly why this algorithm achieves a constant approximation ratio. And for the offline dynamic geometric bin packing problem, the aligning technique is still useful. First, all the large jobs with the size larger than 1/2 are easy to deal with. We just use one machine for each such large job like this. And to deal with all the small jobs with the size no more than 1/2, we first construct the aligned instance, and then we produce a generalized Skyline interval coloring solution for these aligned jobs. And next, we slice the solution into strips, each with a height equal to the machine capacity. For those small jobs fully inside one strip, one machine is used to schedule them, and for the jobs crossing two strips, half of a machine is used to schedule these jobs. Now we proceed to the non-clairvoyant online setting, and we focus on introducing how to deal with the dynamic geometric bin packing problem. It is easy to deal with a special case with the maximum job length delta known as a priori before the online scheduling process, because for each job, we can directly construct and align the job with length being 2 delta in such online setting. Again, we can make sure the aligned jobs are either regular or irregular. And for each job category, we can apply the first fit rule to schedule the jobs onto the machines. which guarantees that an all-meal competitive feasible solution is produced. Well, in the general case, we cannot expect that the maximum job length is known as a priori, but we can take a guess on this maximum job length. That is, at the beginning, the maximum job length is assumed to be the length of the first job, and the aligned instance can be temporarily constructed and scheduled by the same method introduced before. So if our guess is correct, we directly have a factor all-meal feasible solution. And if we guess wrong, we can still double our guess to maintain the feasibility. This guess and double procedure can be done iteratively to produce a factor all-meal solution. In the clairvoyant online setting, the offline aligning technique can still be applied here to produce good solutions. Finally, one open problem is called throughput maximization with bounded busy time. This problem can be seen as a dual variant of the mean usage time dynamic bin packing problem. And this is much about it. Thanks for listening.